Fantastic. Thank you very much. And I just want to also say thank you to Annapurna for providing the venue, providing food and refreshments. It's great, and it helps community in London. My name's Tariq Rashid. I enjoy technology. I have fun with it. I kind of do it as a bit of a day job, kind of. I'm also helping to run the London Python meetup group. Our leader, Antonio, is moving on, so some of us are now going to do that jointly. You're all obviously here because you come through that. So thank you for coming along. I just want to make it really clear that before we kick off, this is meant to be a gentle introduction to neural networks. It's meant for people who want to know what they are but don't already know, or want to get an intuitive understanding of how they work. So if you're an expert, this might not be the event for you. The pictures might interest you, or the Wi-Fi is there if you want to kind of catch up on your emails. So this is definitely aimed at sort of those who are entering into understanding neural networks. So what I'll do is I'll kind of talk a little bit about where AI and neural networks are today as a bit of a context. We'll spend some time trying to understand the ideas, a little bit of the maths that underpins how they work, and we'll use some examples to illustrate the learning points. And those examples may seem noddy, but that's deliberate, so they don't distract from the key kind of the concept that we're trying to understand. I'll talk a little bit about how you might make your own with Python. The focus is on doing it yourself, because that's the best way to learn how things work, rather than sort of pulling in a library and using it as a black box, which you can do. But I think it's valuable to understand how they really work, so you understand what they're good at and what they're not so good at. We'll apply it to a challenge. For those of you who know, there are various sort of data mining, data analysis challenges out there. There's one called the MNIST dataset, which is a dataset of human handwriting, and the challenge is to get computers to learn them so they can recognize them. And we'll even do a live demo, and I might regret doing that, but we'll try doing a live demo where we write a number and we'll see if our neural network recognizes it. Brilliant. Okay. So before I really dive in, I think it's worth sort of getting into the groove of what AI really is. There's a lot of kind of hype around what it is. It's quite cool and sexy. But let's start with a couple of questions. So I said to my daughter's 7, and I kind of showed this picture to her, and I said, could you point to where the people are in this photograph? And she could do that. I mean, she pointed out the children and the person playing the guitar. She even spotted an arm, so she knew there was another person. And she could do that with relative ease. And then I said to her, can you add up these numbers? As a 7-year-old, she can add up. She can add up sort of, double digits, triple digits. She can do that. But she didn't want to do that. And not sure I would want to do that. And if we think back to computers and calculators and calculating machines and cogs and those kinds of things, these kinds of problems are quite well matched to the way computers have traditionally been designed. And like computers find that really easy. It's not really a challenge to get computers to add lots of numbers. But to try and get a computer to attack these kinds of problems is a little bit more difficult. It's been difficult for us to tell computers to program them to solve these kinds of fuzzier, softer problems. In fact, just to put it in perspective, we humans may disagree about the contents of an image, never mind a computer. So that's just to kind of put into contrast two different kinds of problems, those sort of crisp, clear, easily definable problems with something that the human brain seems to be good at, but we've historically not been that good at telling a computer how to kind of solve. And AI is just the umbrella term for those approaches, those algorithms, those recipes for trying to get computers to do more of these kinds of problems, playing chess, recognizing handwriting, driving cars without a driver, those kinds of things. And you'll have seen sort of AI in the news quite a lot recently. Driverless cars. Google's huge announcement recently that it could play Go, the game of Go, sufficiently well that it could beat sort of a world champion. And Go was considered so difficult that it was only expected to kind of have done that in sort of another 5-10 years. So that was a huge achievement with the DeepMind. IBM's Watson's proving itself in the field of sort of medical science as well as recipes. Even your smartphone is getting rather good at understanding what you mean when you talk to it. So that's using sort of some of these algorithms which people put under the umbrella of artificial intelligence. And neural networks are a key kind of element in that mix of methods, and that's what we'll talk about today. So let's go right back to the beginning, start from absolute scratch, absolute zero. Conceptually, we want some kind of machine, a thing, something out of Doctor Who or kind of the Terminator, and we want to ask it a question and we want it to produce an answer. And if you're more familiar with sort of computers and Python coding, you'll recognize the words input, output, and process, calculate. And computers can't do anything more than that. They really are calculating machines. So that's what we have to kind of work within. Imagine we have a really hard problem converting kilometers to miles. It's not really hard, you know that, I know that, but let's imagine it's quite hard. What we can do, a little bit like the problem of recognizing people in pictures or handwriting, we don't know how to solve it properly, but we suggest to ourselves a model which may work. It might be a wrong model, and we'll find out, but we can try a model. Here we have a extremely simple model, which is that the relationship is linear. One is proportional to another. So one is miles is kilometers times a multiplicative factor times a number. So that's coming up with a model which we suppose is really behind this problem. We're pretending the problem's quite hard. And within that model, we have some parameters we can tune and change. In this case, it's just the number we multiply. So we try it. We say, okay, let's just suppose that miles is kilometers times 0.5. So we've got 100, we get 50 out. That was a randomly chosen number. And actually, we know that's not quite right because we compare it to what we know to be the truth. We know the answer should be 62.137, but the answer is 50, so there's an error. So that's not great. It's wrong by about 12. And what we can then do is say, let's tweak that parameter a little bit, see if that works better. Try 0.6 instead, and that works better. The answer is 60, and we know that it should be 62, so it's getting there. That is better. Let's keep going. 0.7, that gives us 70. That's gone too far the other way, and that's worse than our previous answer. So let's go back to the one that was okay and just refine it a teeny bit, kind of calm down our enthusiasm a bit, and that gives the answer 61, which is only wrong by 1.1. So that's the best one yet. So what we've done here is we've picked a model. We're going to try it. We've got some parameters. It's just one parameter here, and we're changing that parameter to see the effect on the answers this machine gives. And you can see that if we carried on playing, we might get to quite a good parameter, which gives us good enough results. Yes, this is an audio example, but the important point is that's how neural networks actually work. The idea of changing a parameter to give us better and better answers is the same. So if we don't know how something works, try a model with some adjustable parameters and use the error to refine the parameter. We use the error to guide how we should tune that parameter, and that's an important point. That's how we train neural networks. We look at the error, we see how wrong they are, and we use that to guide how we might change some of the internal parameters. So that's one of the key points that we should appreciate. Let's shift to another example, outdoors in the garden. Maybe it's because I've got a 7-year-old kid. She goes picking things in the garden. So imagine you've picked up some bugs in the garden and you've measured them, their width and their length. And you can imagine that caterpillars are thin and long, and you can imagine that ladybirds are sort of wider and not very long. And if you plotted your measurements, you might have two clusters, a collection of points here and a collection of points there. And that makes sense. That's kind of intuitive. Now imagine that we wanted to train a computer, some AI, to classify, to predict, to tell us what bug it was based on the measurements. That's not so different from what we were doing before with the conversion from kilometers to miles. If you remember, we had a model which we supposed was linear, a straight line. We can use a straight line to separate off the space which belongs to caterpillars and the space that belongs to ladybirds. So we can try and use the same kind of model to refine a line. So if we've got a line here, a randomly picked initial line, an initial parameter which gives us that slope, we might say, does that work? It doesn't work at the moment because it's not correctly classifying, it's not separating these bugs into the right space. If it was somewhere here, that would work better. This one clearly doesn't work because it's saying that all the bugs are of the same type. That's not right, and that's much better. And the idea is the same. We have a linear model here. We've picked a parameter which is a slope, and we adjust it to try and give us better and better answers. And if we arrived at something like this, that would be a good classifier. So imagine we'd done that. Imagine we did the calculations, and then we tested this thing that we've trained, and we said we've found a bug. Daughter's run in from the garden into the kitchen and said, I found a bug, and these are the measurements. What is it? If this was the line that you arrived at as a result of training, then your machine will be able to correctly say it's in this half of the space, and therefore it's a short, long thing, thin, long thing. That must be a caterpillar. So what we've done there, again, the example's a little bit noddy, but the underlying concept's important, and that is that classification is not that different from what we were doing before, which is using a linear model to convert from one number to another, to predict in some sense. So classifying things is kind of like predicting things. And people do use neural networks to classify things. We've glossed over this idea of learning from data a little bit, so I'm going to zoom into that a bit more. You'll have picked out from what I said earlier that we look at the output from an untrained network or a partly trained network, and we say it's not quite right, the answer should be something else, and therefore we have an error, and I'm going to use that error to improve the machine. We have to have an idea of what the truth should be, what the right answer should be, and quite often we use training data, it's called, examples of data which we know to be true, and we use that to train our machine. So here we have just two items of training data, just to keep it super simple, and I've plotted those here. One's a ladybird, one's a caterpillar. Imagine we have an initial line with a gradient of 0.25. That's not a good separator. We want to shift it up So we need to increase the gradient somehow. We want to get it onto that side of the training data. So we use that point. We take the first example. We say, we've taken the first example, and it's not on the right side of that training example. We want to move it up. So we have to correct that that gradient somehow. And then we can do it again with the next one. Conceptually, that's an easy thing to understand. We're improving the parameter, we're moving it in the direction suggested by the training data. If you want to understand mathematically how that's happening, it's not that difficult if you understand the equations which describe a straight line. So y equals ax is the equation for a straight line. This one's changed. It's the gradient with a bit of a delta. If you do some simple algebra, you can rearrange it to understand what that change should be. That's not that hard. It kind of falls out, and this concept is continued through to the ideas that we use to refine the parameters within a neural network. It's not that different from what we've done here in this oversimplified example. I did something deliberately wrong here. What I did was, again to illustrate a point, what I did was I used one example to update the line, then I used the next one to update it. And if you think about it, if you've got 100 examples or even 1,000, what you might end up doing is you'll end up with a line which only reflects your last data point that you've looked at and ignores everything else. So that's not good, is it? If you've got 10 training examples and you're updating it very eagerly on what your last one was, you might as well not have had the previous 9. So one way around that is to moderate how you update your slope, your parameter, and you can do that by updating it a fraction of what you might have done before. And that concept, a learning rate, has several benefits. One of them is that you reduce the impact of bad training data. If you've got data which is measured wrong, you can reduce the impact that has on kind of perverting what you've learnt. Later on, we'll also see that actually it helps your neural networks learn, but we'll come back to that point later. If we did the kind of calculations, you'll see that actually this time it works better. It's kind of found itself halfway between the two, and that's having a learning rate of a half. So moderating learning is really a key kind of concept, and almost all approaches to neural networks have a learning rate which is not large, sort of 0.1, 0.01. And you actually experiment to see what works best for your particular problem domain. Okay, so that's cool. I'm going to use this example now to try and hit a problem which motivates the reason for having a network rather than a simple node, a simple kind of one function that we had up to this point. So some of you will be familiar with the idea of Boolean logic. If I've eaten my vegetables and I'm still hungry, then I can have ice cream. But I can't have ice cream if I haven't eaten my vegetables and if I'm no longer hungry. And that's an example of and as a kind of logical function. There's another one called or. This is all kind of makes sense in English. If it's the weekend or I'm on annual leave, then I can go to the park. If either of those conditions is true, then I can go to the park. In the first example, both conditions have to be true. So for those, I'm sure many people do know this, but if you didn't know, the word Boolean logic is used there. And this is the same thing summarized in numbers. So we can have two conditions, two inputs, whether I'm still hungry or if it's the weekend. And the AND function is only true if both input conditions are true. And the OR is true if any of the input conditions. So many of you will already kind of understand that and know that. Why have I brought this up? Well, if we're working with data from the real world has nature, physics at play, and sometimes there are causal links between sort of some factors and other things you might measure. If it's sunny, the temperature in London goes up. If there's lots of sunlight, more people might be smiling. So there's a link there, and you can see that you might try to model that data based on those causal factors. And if our learning machines could cope with that, there's a chance then that they could learn that data correctly, so they could predict it. If we draw that picture that we had right at the start, there's absolutely no problem with having two inputs. That's okay. If we used that really simple linear classifier, a straight line, would that be enough? Would that be sufficiently complex to model these kinds of data? Well, the answer is yes, and I'll explain why. If we model visually, graphically, data of that form, you can see that, if we have sort of, two conditions that are true, plot them as 1, 1, colour it green, and then the others as sort of 0, 1, where not all the conditions are true. You can see that a straight line does divide those two classes. So you can see that you could learn to learn data which has that kind of mechanism at play. Similarly with OR, you can have a dividing line which separates those two classes. But here we hit a problem, a historical problem actually, which I think in the 70s made people think there's not much more mileage in this kind of approach. And that's data where the underlying mechanism might be an exclusive OR, where the output is only true if either of the inputs is true but not both. And if you plot that in the way that I've done before, you can see there's no straight line which successfully divides and separates that data. So what we're saying here in clearer terms is that simple classifier based on finding a line, a linear classifier, can't learn to classify data which is has an XOR mechanism underneath it. So that's quite depressing, because lots of data out there in the real world might be like that. We've hit a hard limit. So people sort of said, all right, let's stop funding this kind of research, and a great big important paper was published, which made people sort of think, okay, maybe this isn't the avenue. But actually, if you come back to it and say, hang on a sec, if I used more than one line, I can do that separation. If I have two classifiers, which inside have a kind of a linear function, I can learn to partition more complex data with more complex mechanisms underneath it. That's hopeful. The reason we've kind of taken this sort of meandering journey to this point is this is the motivation for using more than one of those simple classifiers, connecting them together, working together, i.e. a network. And that's why we now have networks of nodes where each of those nodes is there as a simple function working together, because on their own they're not rich enough to successfully separate and learn more complex data. So the learning points there are, some problems can't be solved with just a single simple linear classifier. So you can use multiple nodes working together, ... nodes, a network of nodes, neural networks. Let's take a pause there, because that was quite dry. Let's get back into the real world with how real brains work. So in nature, biological brains appear to have a unit called a neuron, and they have these dendrites and axons and terminals, and what they essentially do is transmit signals. So our brains and our nervous system are composed of essentially these things, maybe different styles of those things, but essentially neurons. And let's kind of put things into perspective again. So I might have a machine with, I don't know how many millions and billions of transistors inside. It's got 512 megabytes of storage. Gigabytes? Yeah, gigabytes of storage. Bloody hell. It's running at, I don't know how many thousands, millions of cycles a second. And yet, a brain which is 0.4 grams of squidgy stuff can learn to fly. That's quite complex. Can learn to fight, escape, communicate, play. It can learn to learn. That's quite complicated. That's quite interesting. So the algorithms that are at play here, the mechanisms of thinking, calculating, whatever's going on in those kinds of brains, is certainly worth investigating and trying to learn from and emulate to see if we can solve some of the problems we want to solve, which we couldn't do traditionally with our traditional kind of recipes. Maybe if we looked at how nature's brains did it, we'd sort of make more progress. This thing's got 11,000 neurons. That's, compared to how many you could fit into one of these things if you wanted to, that's tiny, minuscule. This creature here, again, it can reproduce, it can feed itself, it can navigate, and that has about 302 neurons. Humans have something like 20 billion neurons in our brain and nervous system, so we think we're really clever. But there are species of dolphin which have 37 billion, and they're not using those to type. So you think, what are they doing with those neurons? Because if they weren't using them, they would probably be evolved away because it's a waste of energy. So that's interesting, isn't it? It kind of puts things into perspective. So the reason for me to kind of bring this up is not just to kind of shock us into action, but to make us think, hang on, could we learn from the way nature does calculations, does predictions, learns to react to the environment and do things like fly and navigate and play, and even learn to learn? So there is a biological motivation for some people in exploring neural networks. It wasn't the only one historically, but it was a significant driver for research into neural networks. So those who kind of researched sort of neuroscience understood that those axons, those neurons, what they do is that they transmit a signal, but the way they work is they effectively are a threshold. If a signal is incoming into one of those neurons, the output, it only transmits a signal if the input signal is strong enough. It's almost like saying, I'm turning up the dial and the light isn't going on until I've passed the threshold. So the threshold might be 7 or 10. Once I've passed it, then it'll kind of, the gate opens and the signal is transmitted. So maybe we can use that idea in our kind of attempts at trying to do as well as nature. Functions that kind of reproduce that kind of behavior might be a step function. Turn up the input and then suddenly we have an output. In nature, we don't think things behave quite so crisply. So maybe a more smooth response is kind of a better reflection of what happens in nature. In fact, this function is quite popular in neural networks. It's a sigmoid, it's an S shape, and there's many of those. One of them is a logistic function, it's called, and it's just that simple expression. You can look at the slides later, that they're all online, you can see what that says. That's a popular one because the maths around that is really simple, but there are other ones. There's no reason intrinsically to choose one over another other than convenience, or the maths is easy, or they better match your data. So here's just a picture showing signals flowing through those biological neurons and feeding into others. And you can start to see here that if each of these is a little machine that switches on, if the incoming signal is high enough, we could replicate that. and we've got the idea that there's many connected to many, a network. So suddenly all these ideas coming together points us to what neural networks are today. The picture is just to reassure us that it's okay to have many inputs into one of these computing boxes, circles, and what we're doing is we're going to sum the incoming signals, and if the sum is greater than that threshold, our neuron, which is trying to be like a biological neuron, allows that signal to go through, switches on. We're applying a threshold function. So that's what each of those nodes is doing. So finally, phew, we've arrived at what most people recognize as a neural network. So each of those things is that little node which is trying to be a threshold. We've got signals flowing through. They're all connected to each other. You might say, why are they all connected to each other? They don't have to be. It's just easier if they are computationally. It's easier to code. When a network learns, if a connection was not meant to be, the learning will actually kind of reduce that link. We'll explain how in a minute. So that's the story we've kind of come to so far has taken us to this point. We've understood that there is an input and output to these things. We've understood why there's lots of them, because some data isn't possible to model with just one. And we've understood the biological motivation for this as well. It's worth reflecting back to that example that was right at the start. With that very simple example, turning miles into kilometers, we had a parameter, and we can ask ourselves, what is it that's doing the learning? Well, in that simple example, the parameter is what held the knowledge in some sense. It's what was being changed and refined and improved, just a simple parameter. So it's natural to ask, what is it about a neural network here that's doing the learning? What's being trained? Well, that's a good question. And you might say, is it the function inside one of these things, the threshold function? Is that what we're kind of refining? We're looking at its output. It's not quite good. There's an error. We're going to try and tweak something inside the network. Are we going to change the nature of that threshold function? We could do that. Another approach is to say we're going to change the strength of the connection between these nodes. We're going to have a weight that represents the strength of the connection, and if the weight is high, it amplifies the signal. If the weight is low, it kind of diminishes the signal. So it's almost like a connectionist model. Well, that's an idea, that's an approach. As it turns out, that's the approach that's predominant. It's the one where we adjust the strength of the links between those nodes. It's not the only approach, but that's what most people would do. That's what most people understand when you say neural networks. So, let's work with some numbers. So if you imagine we've got a simplified neural network and we have some input signals. Could be the measurements on bugs, could be the color values from a picture perhaps, and those are the question we ask of our neural network. Those numbers are put in as inputs and they flow through the network and give us an answer. At the beginning we had a very trivial calculation to do, a multiplication. Here we're propagating that number through, but we're applying a weight. So if the weight is 0.9, it's kind of hard to see there, so 1 times 0.9 is 0.9, and that's what emerges at the end of that connection and goes into the next node. This weight is 0.2 between that and that node, so 1 times 0.2 is 0.2, so it's been diminished quite a bit, and that's what travels down there. Similarly, we've got a value here, 0.5, and we've got the weights here, 0.3 and 0.8, so 0.5 times 0.8 is what travels along there. And you can see that each node then has several incoming signals, and again we add them up and feed the signal forward, and we can have many layers. So the point of this slide is just to explain, just to really make it clear, what's happening to numbers as they flow through a network. So that wasn't that hard, that was kind of easy. Sometimes that picture can look quite daunting, oh my god, but what's happening is it's just as simple as numbers being multiplied by the weights and fed forward. So just to refine that picture we had before, we've got the inputs, but we've got weights now, which either emphasize or de-emphasize those signals. So we've got a sum, which is A times that weight, B times that weight, C times that weight, and any more that you might have coming in. Cool. That's, if you wanted to do the calculation, those are the answers you'd get. Now here's an interesting point. If I wrote down with a pen and paper, algebraically rather than numbers, what's happening, if I looked at that point there and said, the thing that's arrived here is this signal, input 1, times that weight, plus this signal times that weight, I've written that out. And if I do the same here, the signal here is that input times that weight, that input times that weight, added together. If I did that, and if I did it for kind of maybe more, sort of bigger networks, I start to see a pattern. You can probably see it already. But it turns out, really conveniently, that those expressions for the signals that arrive at a node can be written as a matrix multiplication. Some of you may say, oh no, matrices, I hate them, boring. and I don't blame people for thinking that, because schools don't do a great job of enthusing people. Who enjoyed matrices at school? Oh, you're atypical. But it's really a nice coincidence that, you know, if we had a matrix of weights and a vector of the incoming signals, and we did a sort of a matrix multiplication, we end up with those expressions for what's coming into a node. And you might say, so what? You know, what's so cool about that? Well, there's two nice things about that. One is that we can write what's happening really concisely. You know, imagine if I had a 20 by 30 or a 200 by 500 network, I wouldn't want to write all that. So I can write it in a much more sort of concise form and not worry about the actual size of that network. So that's nice for me because it saves my handwriting and just easier to write. But also, some programming languages, some computer programming systems, recognize matrices and can do them efficiently. They're optimized for doing matrix multiplications rather than sort of doing each one. They might parallelize them. They might recognize there's actually what you're doing if you do the calculation is lots of the same sort of thing, and that's great. In fact, lots of machine learning today takes advantage of the fact that both software and hardware can be used to really accelerate these kinds of calculations. So you'll have heard some people use their graphics card to do kind of machine learning. You're offloading these kinds of calculations onto your graphics card, which can do lots and lots of these calculations in parallel, for example. And if I'm programming, I don't need to say, you know, variable 1 times variable 2 plus that times that. I don't need to make lots and lots of explicit instructions. I just write this, and the programming language understands that, and Python's NumPy understands that. There's a question over there?
Yeah, just a quick one. On that previous page,
yep.
Are you not doing a function on the input as well inside the node and then doing times by the weight? Is it purely just the input times the weight? Or?
Yeah, it's just the input times the weight for all the inputs coming in, and then I apply the S-shaped function, the threshold afterwards. So
at what point do you do the S-shape not on each node then? Or?
You do it on each node, yeah. What if you did this, if you did the kind of the matrix approach, you'd end up with a matrix of the incoming signal before that the threshold function was applied, and then you apply that element-wise. That's an easy thing to do. In fact, I'll show some code later. It's super simple. But you're right to point that out. There are actually two steps there. One is the summation of the incoming signals moderated by the weights, and then we apply the threshold function to understand what comes out of that node. So we do those two things.
Okay, thank you.
Cool. All these slides are online. They will always be online. I won't take them away, so don't worry if you can't read some of the writing there. Okay, so that's cool. That's exciting. I find it exciting. Another interesting question to ask is, when we had that simple trivial example of the kilometers and miles, we had a single node with a very simple expression inside it. That model was a linear model, and the algebra for turning the error into a weight adjustment, a slope adjustment, was quite easy. What happens when we've got a whole network of these nodes? What error do we use? If we looked at the output layer, we know what the answer should be because we've got training data. We say for a certain input the answer here should be a 5 or a 0 or a 1. So we know what the error is here, and we can use that to kind of update the weights in there or do some kind of refinement. But what's the error in here? What's the error somewhere deep in the network? Well, that's actually not a silly question. And it's one actually that, again, historically did hinder the progress of neural networks. And it took some bright spark to invent an interesting way of addressing that. But if you think about it, what do we do with the error? Do we kind of split it and push it back? Do we say, I don't know, if I've got an error of 10 here, do I split it evenly across all the incoming nodes? Well, you could do that, because you might say they all contributed to the error. We might say, actually, I'm not really certain, because that might have had the perfect weight, and that was the right answer, but that one was wrong. But you don't know that, actually, when you're training a network. So you can only have a kind of a heuristic approach. And one heuristic is to split it equally amongst all incoming nodes. Another heuristic, which is slightly more sophisticated, is to say, let's split it in proportion to the weights. So if we've got weights 3 and 1, we might say, let's put 3/4 of the error in that direction and 1/4 in that direction, and that's an approach. And that seems to work. The rationale for it is not solid. It's a heuristic, but it seems to work. That is blurry, isn't it? What's happening here is we're seeing those errors split and fed back down into the network. So if we had an error of, say, 10 here and split it, 7 and 3, let's say, that error of 7 is pushed back to that node. And similarly, the split error from another output node is pushed back and recombined. So that's one approach to back propagating the error, and that's where the term back propagation comes from. I won't do it now, but if you wanted to later, you can see that the numbers work. We've split the error here, 1.5, according to the weights, and then we've recombined it. And again, if you fancied writing that out in terms of sort of variables, you'll see again that the error at an internal node can be written as a matrix multiplication of the weights and the error on the other side of that node. And that's great, because again we can accelerate those calculations. Okay, so we've got the error. How do we actually update those weights? This horrible expression is what pops out of that neural network at an output node as a function of the weights. That's horrible. So we're not going to untangle that. So again, let's see if there's another kind of a creative way of doing that, or even an imperfect way of doing that, but that's good enough. So I'm going to shift us again, not to the garden, but further afield, and imagine that we're sort of in some dark sort of Welsh hills or some Scottish hills. Imagine that we've got that horrible function. Imagine if you've got any kind of horrible function that's not easy to do kind of algebraic analysis on, so we can't algebraically work out where its maximum minimum is and so on. And what we perhaps want to do is find where a minimum is. If you were really out there with some hills and you didn't have a map, so you didn't understand what the function worked like globally, what you would do is you might switch on your torch, and it's dark, so it's representing the fact that you don't understand the whole function. You switch on your torch and you kind of look around your own feet and you sort of say, all right, there's a downward slope there, I'll take some steps in that direction. And if you apply that approach, you'd eventually kind of get to of that function, of that landscape. That gradient descent is actually an approach people do apply to working out how you might get to the bottom of a complicated function. You might say, what's this got to do with neural networks? I'll explain in a minute. But let's just linger on that a little bit further. If I've got a very simple example here, imagine that's a complicated function, but it's not really. Again, we've just got a quadratic here. You can see that if I kind of landed somewhere, started at a random place, and looked at the gradients, and then followed the downward direction, you could see that if I did that repeatedly, I'd get to the bottom of that function. Now, with this example, a quadratic function, that's easy, we know how to do that. But if there was some horrible complicated function, this approach would give you good results where the function itself was too kind of complicated to kind of unpack kind of algebraically. So this is called gradient descent. And the connection with neural networks is, if this function was the error of that neural network, a horrible function, as a function of the weights, so given some weights, we have values, and we vary the weights, and it kind of behaves in kind of ways that aren't easy to understand. We could use this kind of approach to get to the bottom of that function, i.e. to minimize the error. That's what we want to do, remember. We want to minimize the error. So that's why you'll hear gradient descent being used when people talk about training neural networks. I'm conscious of time. Can we have 5-10 more minutes? Yeah, cool. I enthuse myself about this and I forget everyone's listening. Cool. So that's my attempt at trying to visualize that. We've got some kind of function landscape with all sorts of lumps and bumps, and what we want to do is get to the bottom of it. And if that function was the error of that neural network, and that error obviously depends on the weights, so you change the weight, you kind of end up somewhere else. We want to find which weights minimize the error, and that's what you're doing when you're training a neural network. You're adjusting those weights so that your overall error is minimized. And the way we do it is we take this good enough approach of getting to the bottom of that complicated function. So you see here we've used the idea of calculating the slope. So there's an interesting, someone challenged me, a good challenge the other day. They said, hang on Tariq, you said this function was complicated. Yes, it's complicated to the extent that we couldn't analytically work out where the minimum was, but it's not so complicated that we couldn't work out the gradient at a particular point. And luckily, that's often possible, and is possible if we have an error which is, the desired output minus the actual output, and we square it so we don't kind of worry about negatives. And the calculus to get from there to the error depending on the weights is not that hard. I didn't do it here because we're short of time, but just to reassure you, it's It's just the calculus chain rule. So some of you will remember that from GCSEs, O-levels, A-levels. It's nothing more complicated than that. And it's a terrible shame that lots of the textbooks out there kind of make a real kind of meal of it. But you could do this in just 2 or 3 steps. So it's not that complicated. So what we've got here now is an expression which tells us the gradient of that function. There's a link here to a blog post I did. If you're new to calculus, it explains it in a gentle way if you want to have a look at that. So what we're doing is we now have an expression which allows us to update the weights. We've got the old weights, we've got an error because we've compared it with the training data, and we want to use that expression that we calculated just there to update the weights. And we don't forget there's a learning rate to kind of moderate the learning. The second reason why having a learning rate is good, it wasn't a cop-out before, is that if the learning rate is high, you can end up jumping about the actual minimum. You can take a step in the right direction and overstep where you want to go. So if you turn it down, you can have smaller steps, so you're more likely to get to the actual bottom. Cool. So that's all the theory behind a neural network. If you wanted to make your own, it's not that hard. You can imagine a neural network kind of class, and what you would need to do with this class is initialize it with initial weights, random weights. You'd want to train it, and then you'd want to query it. Conceptually, that's all you'd need to implement. Some people do more, but you know, if you wanted to do this yourself, there are really only 3 kind of core functions that you'd have to think about implementing. So let's talk about them very briefly. You're initializing your weights, and you might ask, what are the initial weights? They're random. If you want to be more sophisticated, you don't want them to be too big, so maybe random between 0 and 1. You can be more sophisticated than that. Look it up. Some people use normal distributions to subsample from, but you don't have to really. It kind of works. We've talked conceptually about how we do the learning, and the querying is actually simpler than the training because we're just pushing values through. It's worth kind of mentioning some of the Python, because it's a Python group, some of the Python libraries that help. NumPy is really cool because it allows us to do all the matrix multiplications, and it kind of accelerates that, and that's nice. There are other things I've used for visualizing pictures. The SciPy kind of collection of functions has things like the logistic function, the S-shaped function in there. And I've discovered notebooks. You might say, that's really cool, but I started Python in 1997, so we didn't have the idea of kind of web interactive notebooks there. They're cool for me. So as you can see, you can have a look at this later, you know, at your own kind of time. But just to show you how simple it really is, this is just the initialization function of a neural network, and we've given it parameters of how many input nodes, how many hidden nodes, the middle layer, how many output nodes, and we're using those to define a NumPy array of weights, and I'm using sort of sampling from a random sort of normal distribution, and it's as simple as that. It's not much more complicated. I've set a learning rate. I've got the logistic function from that SciPy module. Super simple. Querying, you asked earlier, is as simple as pushing values through those layers of a neural network. So we have some inputs. We've done the dot product to multiply the matrices to work out what the inputs are at the next layer. We've applied that threshold function, and I'm doing it again because I've got another layer. It's a 3-layer network, and then that's the output. It really is as simple as that. I've got a lot of code here. Some people can write it much more concisely. I can take away the comments. So you could do this in about 3 lines if you really wanted to. The training function looks scary when you look at it like this, but then you realize that the first half of it is pushing signals from the start to the end of the network, so it's the same code as before. So the only bit that's different is this bit. Again, it's about 4 lines of code. We've taken the error, the difference between the targets and the outputs. we've done that matrix multiplication to work out what the errors are at internal nodes, and that long expression here was that expression we worked out through calculus, and it's as simple as that. I will zip through the next bit because that's the visual bit. There's a handwriting challenge, as I said, called the MNIST data set, and it's got 60,000 of these kinds of numbers, and they're labeled so you can train your algorithms to kind of try and learn them. The standard set comes with 10,000 test examples, and what people do is they write their own algorithms, whether it's a neural network or something else, and they compare how well they do compared to everyone else. So it's a common, popular data set, and if you kind of download it and have a look at it, it's a string of numbers, and what it is the first number in a line is the label. Is it a 5? Is it a 6? It's a 5 here, and the rest are the pixel values. And if you push that into a neural network, 3-layer neural network, we can try and train it. I'll skip over this slide because it's a short time. And what you find actually is, with just the simple ideas that we've talked about here, nothing overly complicated, no fancy kind of optimizations or extra kind of, cool kind of activation functions or fancy error functions, just the stuff we've talked about today, you can get really rather good results. With just a few lines of code, you can get 96% accuracy when you test against that data set. So 96% accuracy over 10,000, that's not bad for a bit of code, about 20 lines of code, to learn human handwritten characters. There's some experiments here playing with the number of hidden nodes, how deep that network is, sort of how big that network is. We can play with the learning rate, and you can see that if you have a high learning rate, your performance drops off because you're overstepping the minimum of the function. You can reuse your training data, and up to a point, that kind of improves your results. So 96% is really kind of cool. But you can even go beyond that. If you sort of understand that what we're looking at, if you understand your problem domain, you understand your data, you say, hang on, these are handwritten numbers, so some people write them at an angle. Why don't we augment the training data by adding to it rotated versions of itself? So we say we've got an original, and we take 2 more of those, we rotate them one way or another. So we've tripled our data set, and you can boost your accuracy to 98%. These numbers are kind of in line with what the professionals would end up with. I mean, there's people out there who can get it to 99.5%, but they go to an inordinate kind of complexity in their approach. So that's not bad. I will stop there, but who wants me to do a live demo? By the way, you can do all of this on a Raspberry Pi, which costs, the Raspberry Pi Zero costs £4. And I've tried it, I've proved it, you can do that. So it's a good project for kids. Let's see if we can do a live demo. This is where I get embarrassed if it doesn't work. So I've got a network that I trained just on that MNIST data set. I previously had a 2, and the network said it was a 2. What I'm going to do now is think of a number. Give me a number. 7, okay. Right. This all could go to pot now, couldn't it? I was hoping you'd say 3, actually. All right. Let's try 7. Let's really push it. Let's resize that to the size of our network, which is 28 by 28. I'm going to save that. And then, the moment of truth, yep, network says 7. Phew. Yeah. Actually, 7 was the one it found hardest. It finds things like 1 and 3 really easy. Phew. I skipped over a few things there. If you want to know more, come and talk to me. I'm on Twitter a lot. You can email me. There are some links that you can have a look at on those slides. If you want to know more, there's a little guide I've written which goes even slow if you want to. But I hope you kind of enjoyed that. I hope you took something away from that. Thank you very much. Do we have time for answers or questions? All right. There might not be any. Go on then.
So I've already asked a question, but how do you choose the parameters? Can the machine do that, or do you have to manually do it yourself?
When you say parameters, do you mean?
Like with the caterpillar example, you can clearly see like weight, like length, diameter, or something.
Yeah.
So something like 7, it's a bit more abstract.
Yeah.
Like if you're trying to choose images on a picture, then it gets.
Yeah. So there's a whole different art of trying to find what the right features, as they're called, of your problem domain, what the right features should be to maximize your learning, and that's an art in itself. So I'm not going to say it's easy. Sometimes you don't have much choice. You have the data that you're given, and you have to make the best of it. So you might say, I've got something floating around in space, and it's giving me values for electricity consumption, temperature. This is actual challenge from the European Space Agency. So sometimes you don't have a choice on the parameters, but where you do, the short answer is you experiment to try and work out what the most useful features are. Sometimes you can use your understanding of the problem to think, well, hang on, I know something about the problem domain, and I know, for example, that it might have sort of rotational invariance. It doesn't matter which way I look at the problem, and therefore I might reformulate my input parameters to be, I don't know, radius instead of xy, and that might be more useful for training. So there's no straight answer, but it's an entire field of study actually to understand what are the best ways of arriving at the most useful features. And sometimes you don't have a choice. Sometimes you have to experiment, and sometimes there are things that people do that too advanced for me to understand.
Right now, is that generally done by people though, or some of the more advanced learning algorithms?
Yeah, you can automate part of that process. You can automate the trying of different parameters to understand which ones are the most discriminative, the most kind of useful in helping your thing learn. And there are some automated ways of doing simple transformations to say, if people understand things like principal component analysis, can I shift and rotate my data to kind of make it the most, can't think of a better word than sort of.
Explain variance.
Yeah. So it's there are approaches you could do that, but it's not a completely solvable problem. There's always going to be an art to it as well as a science.
If I may add, so usually you collect everything that you can, and then basically if you have enough computing power, you just rank on everything. But if you're doing biomarkers, something which is extremely expensive, you do it before you do any type of neural networks or whatever you're going to use. You do experimental design things. So you design experiments to see what potential biomarker could be, and then in the end it's just about cost-benefit analysis. So sometimes you lose a little bit of precision, but it's cheaper to collect these features than those features, and so on. So it is an art, but also there's a huge field of experimental design that is basically developed just for this, to find features which might be useful.
Absolutely.
But Google doesn't do that. It just collects everything more or less. It's got enough computing power to run it. If you're doing it at home, it could be a problem.
Yeah.
If you have a cluster.
Yeah. Just to kind of add a little bit more to that, people talk today a lot about deep learning, and people understand different things by what that means. If you look at the example I used with the pixel values which describe those numbers, I've not really treated those pixels in any sophistication. I've just dumped them at the neural network, and it worked. I knew it worked. But if you kind of have more sophisticated image recognition systems, what they will try to do is not treat every pixel equally, but try to pick out features that the analyst or the scientist or the coder has arrived at as being useful. So we know, even from biology and the biological inspiration, that our eyes and brains respond particularly to textures vertical lines, circles, patterns, spots, and if you can have an intermediate step of picking those out and then feeding that into the next step in your learning pipeline, so you can have a hierarchy of features, sort of low-level pixels, next level of shapes, next level of sort of composite objects, then that seems to be an approach that works better than simply having a shallow approach of here are all the pixels, try to learn on it. So that's kind of one way of understanding what deep learning is. It's actually a hierarchical approach. I hope that kind of adds to your question.
Yeah, thanks so much.
Cool. Right. Go for it.
Yeah, I would like to know, when do you think a neural network is better than another algorithm, like a random forest? Which kind of domain, which kind of data do you think a neural network outperforms?
So, if I'm honest, I don't know. But I will try and answer it, and I did a master's degree in this years ago, so I'm trying to kind of think back to then. Each of these algorithms are good at different kinds of things. So what neural networks are actually doing is adjusting some of those functions, and you might have problems where that doesn't help. We had the very simple example of a linear partition with more sophisticated activation function, that threshold function, it's a curve, and you have combinations of those, so you can see that you might be slicing off with lots of curves your problem space. If you know that your problem is amenable to that kind of slicing off, then neural networks might be a good approach. Actually, I'm not going to attempt to answer your question because I really am not qualified. If other people know, please do chip in. I don't know what a random forest is.
I think the appeal to neural networks is just that they're very expensive, but they're also very scalable. So if you have the hardware, just for hardware, what GPUs, 2,000 processors, neural networks can help.
From my perspective, they're good if you just want to know the answer, but they're not so good if you want to understand why. So the answer pops out as 7 or whatever it is. Why? It's a bit of a black box.
The same thing is with random forest. So all modern techniques basically don't give you feature selection, can't really explain the things that are done again with experimental design. The thing is that if I were using it, I would start with random forest definitely because it's a simple model, it's extremely simple, and it works out of the box. And then if you need to dive into it, if you need to create he said, more scalable solution that is adjusted to something special, I would go to neural networks. But as like the first thing, I would start with random forest. It's bootstrapping, it's extremely simple, it's fast, it's easily parallelizable, it just works out of the box. If you just find to see if there is anything there, then.
Yeah. Let me show you a picture, if it pops back up. Sorry, Harry. I'm torturing you, aren't I? Most people use neural networks forward. They ask it a question, they pop an answer out. I don't know why many people don't, but you can go backwards. If you have a trained neural network, you start off with the answer and ask it what the question should be. That can sometimes be quite enlightening about your problem. I tried it with these numbers, and that looks like a mess. Is it an X-ray of a brain? I don't know. But actually, if you stare at it for long enough, I did, it starts to make sense. So this is what you get back out as the ideal question for the answer 0. You can see there's a circular kind of a shape. You can see there's dark bits and light bits. And what that really means is, what the network has learned is if a pen has marked anywhere in the dark regions, that's supporting evidence for a 0, combined with an exclusion from the white bit. And you can see that with a 3 as well. Is that a 2? That's a 2. There's a 3. You can see there's exclusion bits which are inside the lobes of a 3. So this is just an interesting experiment to see, well, what has it learnt? What does it tell me about the problem? And in other problem domains, that might be quite enlightening. I will stop there, Harry, sorry. Cool. Should we call it a day? Thank you very much. I'll hand back over to Annapurna. Thank you.
So Massive. Sorry. Thank you to Tariq for an amazing presentation. Unfortunately, way over my head, but I'm sure some really interesting points that you found from that as well. I'm sure Tariq will stick around afterwards for anyone that's got some more questions as well. We've got some more pizzas that have arrived. Hopefully they're still warm. And also there's plenty more to drink as well, so please feel free to stick around and chat some more about this. So once again, thanks very much to Tariq. I'm sure you'd like to join me in saying a massive thank you, and thank you all for coming tonight as well.